Okay, so Michael asked if we can go over the multiplication rule. So let's take a look here. First of all, we should talk about independent and dependent events, and just to make sure that's clear. So independent events are when the probability of one event occurring has no effect on the other event occurring. So, two unrelated events would be considered independent. A dependent event would be the probability of one thing having an effect on the probability of another thing happening. So in this case, we're talking about health insurance and poverty. So we could say that poverty and whether you have health insurance or not are dependent events, because the effect of because being poor has an effect on whether or not you have health insurance or not. And we can calculate whether two events are independent using this formula. So if we have the conditional probability of the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B, we know mathematically that these two events are independent. And if this is not the case, we know that they are dependent events. So we like independent events because they're easier to work with as far as calculating joint probabilities is concerned. So if we have independent events, we can just multiply the unconditional probabilities in order to calculate what the joint probability is. So for an example, if you have events A and B and they're both independent, then the probability of the joint probability of A and B occurring is equal to the probability of A multiplied by the probability of B. But this is a strong assumption. This does not always take place because events are rarely independent in reality. So we're typically dealing with dependent events. So in that situation, we can therefore use the multiplication rule. Because events are not always independent, we have the multiplication rule of probability, which we can use to find these joint probabilities. So we can describe the multiplication rule to find the joint probability of events A and B as the probability of A given B multiplied by the probability of B. So you see here we're using conditional probability to calculate the joint probability here. And similarly, we can also use this formula, the probability of A and B. So it's the same joint probability that we're calculating, but we're calculating it just another way as saying probability of B given A multiplied by the probability of A. And the multiplication rule can help us find the joint probabilities when we have conditional and unconditional probabilities, both. So if they're independent, this actually simplifies because, as we saw before, that if A and B are independent, then the probability of A given B is just simply the probability of A. Then the multiplication rule just simplifies to the probability of A and B is equal to the probability of A times B. So if you're dealing with independent events, it's very, very simple. It's just the probability of A multiplied the probability of B. That will lead you to the joint probability between these two events. If you're dealing with dependent events, then you're going to have to use this multiplication rule to find the joint probability. So just be mindful that if you can first find out whether these are independent or dependent events, you can then use one of these two formulas. You could use either two formulas. This formula is going to work in either situation, and it's just going to simplify in the case of independent events. But just know that if you have you have dependent events that you're dealing with, you're going to have to use this multiplication rule. You can't just plug it into this simplified rule. Otherwise, you come up with the wrong answer. And so here, we're talking about the conditional probability of an event, which is given by the probability of A Yeah, Michael, can you is the formula being displayed on the screen here? I just want to make sure that I'm missing. Can you see this formula here? The probability of A and B is equal. No. Can you? Is my screen being shared at all? Can you guys see it? So Ruji can see it. Let me see if I can try to share it again. Let me see if this will work. So I just tried to share it again. Are you able to see it now? It's page 91 of the lecture notes. Okay, now you can see it. Okay, great. So as we were saying, so this is the multiplication rule, which we're using for dependent events in order to calculate the joint probability of both events occurring at the same time. So we can use this formula. Probability of A and B is equal to the probability of A given B multiplied by the probability of B. Or similarly, to say the probability of A and B, so this is the joint probability, is equal to the probability of B given A multiplied by the probability of A. So is that clear that we're going to be using this formula when we're dealing with dependent events? And that is, and let's just go over this slide again. So this is what happens when we're dealing with independent events. And if we're dealing with independent events, then the conditional probability of the probability of A given B is just simply simplifies to the probability of A. So if you plug that into the multiplication rule, it simplifies with independent events to just saying the probability of A and B is equal to the probability of A multiplied by the probability of B. So if we're dealing with independent probabilities and you need to find the joint probability between those two events, you can just simply multiply the two probabilities together and find your answer. If you're not dealing with independent events, then we have to use the multiplication rule. Does that make sense, Michael? Just want to make sure everyone's on the same page here. So this is the formula that we'll use for dependent events, the multiplication rule. And here we can look at this slide. So the conditional probability of an event is given by the probability of A given B is equal to the probability of A and B divided by the probability of B. So this is how we calculate the conditional probability of A given B. And hopefully this notation is clear. When I say, when it's written like this, the probability of A and then has this line here and then B, this is to say the probability of A given B. So given that B occurred, what is the probability of A occurring? This is how we read this notation. And we calculate it as the joint probability of A and B occurring over the probability of B. And then similarly, we can look at the probability of B given A is equal to, again, the joint probability of A and B occurring, but now it's over probability of A because it's given that the event A is occurring. And like we said here, we could also look at it this way. So if we have independent events, and it's just saying the same thing, we're just reiterating what was said in the last two slides, but in different matter here. So if we have independent events, then we can simplify the probability of A and B is equal to the probability of A and times B. And we can calculate that. Yeah, so you're only going to use this multiplication rule of in this format for dependent, if you're dealing with dependent events. So only if you're dealing with finding the joint probability of two dependent events. If you're dealing with independent events and you're trying to find the joint probability of the two, if they're independent, you can just simply multiply the two together. But if you're dealing with dependent events, you're going to have to use this formula here. The probability of A given B multiplied by the probability of B. And this is just to show as a proof that if we look at independent events with this conditional probability formula, the probability of A given B is equal to the probability of A and B over the probability of B. And here we're just substituting in the probability of A and B as the probability of A times the probability of B, because they're independent events, over probability of B. So in this case, the two probabilities of B in the numerator and the denominator, those are going to cancel out. So we're left with a conclusion of the probability of A given B is equal to the probability of A. So conditioning on B doesn't give us any more information about the probability of A if you have independent events. So does that clarify it a little bit more, Michael? We can give more examples and work them out together. It might give us a little bit more. Might become a little bit more clear. Let's take a look here. So let's use this example. So let's use this example and let's work on this together. So this is a question where we're going to use our probability rules. So let's take a look at the question. It says a bag contains 6 black marbles and 4 blue marbles. 2 marbles are drawn from the bag without replacement. What is the probability that both marbles are blue? So how would we go about answering this question? Let's try to work on this together. So let's take this step by step, right? So we're saying here, how many marbles are there total in, can everyone see the question on the screen? Okay, great. So let's try to work on this problem together. So how many marbles are there in total? 10. And there's 6 black marbles and 4 blue marbles, correct? Okay. And the question is asking us, what is the probability that both marbles are blue, right? So how can we answer this question? Well, let's take a look at the events, right? There's 2 probabilities here. There's the probability, so if you put your hand in the bag and you pick a marble out, there's 2 probabilities, right? And we can calculate those 2 probabilities. What are the 2 probabilities of that event? What are the 2 outcomes? Yeah, exactly. It could be either blue or black. So what is the probability of you getting a blue marble, and what is the probability of you getting a black marble? Let's just write out those probabilities just so we can work that out together. Four tenths and 6 tenths. Correct. That's right. Now, that's the probability of us getting a blue marble or a black marble the first time, right? So us putting our hand in the bag and pulling out any random marble, that's going to be our probability of getting either a blue marble or a black marble. But what is the question asking us? It's asking us about picking up 2 marbles from the bag. And it's saying without replacement, meaning that if you take a marble out of the bag, you're not putting another one back in. Once you take it out, it's not being replaced, right? So let me ask you a question. If we look at these 2 events, right? We're putting our hand into the bag and picking out a marble. That's one event, right? And then we're putting our hand back in that bag and picking out another marble, right? So those we can look at as two different events. Now, are those events, are they dependent or independent on the probability that they both are blue? Which is to say, is the first event, the probability of the outcome of that first event, is it going to affect the probability of the second event? Are they independent events or are they dependent events? They're dependent events, right? And is it clear why they're dependent events here? They're dependent events because if you take out a blue marble on your first draw, that means that you were successful in that event, but now there's one less blue marble in the bag, right? So during that second draw, it's going to be the probability of getting another blue marble is going to change from the initial probability, right? So here, what is the question asking us, right? It's asking the probability of both of the marbles being blue, right? And if we talk about that in probability speak, right, given that we have two events here, we could say it's the probability of getting a blue marble on the first event, and so it's the joint probability of getting a blue marble on your first draw and a blue marble on your second draw. So we're looking at the joint probability of those two events occurring. So how would we calculate this given our multiplication rules, and how would we come up with the answer? And here I can okay, so let's look at this here. So I pulled up the question and I pulled up the slide about the multiplication rule, right? So we said here that the probability of events is given by the joint probability of dependent events is given by the probability of A and B is equal to the probability of A given B multiplied by the probability of B, right? So let's just start off by stating what the probability of A and B is in this example. So what are we going to label probability of A? What are we going to say probability of B is? Okay, so Michael said the probability of A is the first marble being blue. Yep, that's absolutely correct. What will probability of B be? Do we know what the probability of B is? Well, let's think about it again. So it's asking us to find out what the probability that both marbles are blue is. Right, so you got it, Michael, exactly. Probability of B is the second marble being blue, right? And here we're gonna calculate the joint probability of the two. So in other words, we wanna know what the probability that both of the problems, both of the marbles being blue is, right? So we can list this out. So we already said that we said what is the probability of A? Let's just write out what that is. I think Ruji already said what the probability of A was. Let's just reiterate what that is. Four tenths, right? So now we know what probability of A is. So we can look at this formula here. Yeah, exactly, Michael. So let's look at the second formula here. The probability of A and B is equal to the probability of B given A multiplied by the probability of A. So let's put this in other words towards this example. So the probability of getting two marbles that are blue is equal to the probability of the second marble being blue, given that the first marble was blue, multiplied by the probability that the first marble was blue. So does that make a little bit more sense now that we can look back at the formula and put our example in? So we're saying that the probability of these two marbles both being blue is equal to the probability that the second marble is blue, given the first one was blue, multiplied by the probability that the first marble was blue, right? So we already know what probability of A is. We said that's 4 tenths, right? So how do we calculate this probability? The probability of the marble being blue, the second marble being blue, given that the first marble was blue. How do we calculate that? We could think it through. So we had 10 marbles, 6 were black and 4 were blue, right? So we already said that the probability of the first marble being blue was 4 tenths. So let's say you succeed and you got a blue marble. So Fatima, you think it's 3 tenths, right? Does anyone else have an idea, I guess? So Michael got it right. The probability of B given A is 3/9. One less, correct. Because we put our hand in the bag, right, and we pulled out a blue marble, and that was blue, but we're not replacing it. So that marble's being, say throwing out that marble. So now you have one less blue marble. So now you have 6 black marbles and 3 blue marbles, right? So that totals 9. And then on the second event, the second try, the probability of getting another blue marble is going to be 3 out of the total, which is 9. So 3/9, right? So now we're pretty much almost done with the problem, right? We're basically almost at home base. We just have to put it all together now, right? So how do we calculate what is the probability that both of the marbles are blue? We just have to multiply them two together, right? So why don't we do that? and see what we come up with. You might need a calculator. Depends on how you want to do it. We could say 4/10, right? Yes. Yeah, so you got it. So you're just multiplying the two together. So it's 4/10 times 3/9, right? Which Michael said is 0.1333, right? You can also leave it as a fraction. It's actually 2/15. So that's how we'd complete this problem. And does that make sense? Was that difficult? Does that help kind of clear up how we think about the multiplication rule in this example? And just to reiterate, we use the multiplication rule here, right? Because we have dependent events. So because the first event was dependent on the second, we had to use this multiplication rule with the given probabilities. Because the probability on the second event was conditioned on the probability of the first event. So that's why we had to use this multiplication rule. If they were independent events, we could just simply multiply the two without conditional probabilities. So in that case, it would be kind of like what, it would be, let's say if you had replacement, let's say if this question was asking the same exact question, but it says that you were replacing the marbles after each draw. So after the first marble that you got a blue marble, you were putting that marble back in the bin, in the bag, and that's with replacement. If you had that question, that would mean that you had independent probabilities, because the probability of drawing a blue marble on your first draw would have no effect on drawing another blue marble on your second draw. So those would be independent probabilities. And then you could just simply multiply the first probability, which we said was 4/10. We could just multiply 4/10 times 4/10. But that's why we want to make sure that you don't get confused here, because if someone might be reading this question quickly and think, and they might oversee that concept that there's without replacement in this example, but they might just multiply the two together. So that would be the probability of getting two blue marbles if you had replacement. If after you took that marble out, you put it right back in the bag again, that would be independent events, and that would just mean that you would have to multiply 4/10 twice. But in this example, because you don't have replacement, you're taking that marble out, that means that the first event the second event is dependent on the first event. So the probability of drawing a blue marble the second time is dependent on whether you drew a blue marble the first time, because there's replacement. Yeah, so we could definitely do a relative risk question for sure. So here we go. So when we talk about relative risk, it's important that we understand what relative risk is. So first of all, it's used often in medical fields and biostatistics, specifically when we talk about a disease state and an exposure. So the classic example that I like to talk about is whether you're a smoker or not, and whether you develop lung cancer. So in this case, we would say the smoking would be the exposure, and the event would be developing lung cancer. That would be the disease state. But also in sociology and psychology, we can also look at exposure not being, let's say, smoking or you know, getting x-rays or something like this, or radiation. We can actually look at it in a different way and saying that exposure can be exposure to poverty or to some other conditions. And we can use events like having health insurance or not in this example, or you know, we can look at if someone's born into poverty, will they become poor as an adult? So we can use that as the exposure in the event. So it's important here for us to first, as a first step when talking about relative risk, defining what our exposure is and defining what our event is. So just so that it's clear, because sometimes I think people might be confused on what the exposure is and what the event is. So we just want to make sure that we clarify that the exposure is what's going to lead to the event happening. And because we're looking at an exposure event and exposure to a given circumstance and the concurrent and then the event that occurs after that, we're dealing with conditional probabilities. That's basically the definition here. And we calculate relative risk using this formula here. Can you see this formula, Michael? It's relative risk is equal to the probability of an event occurring given they were exposed over the probability of an event occurring given they were not exposed. So we're looking at the probability of an event occurring in these two different groups. The one group is those who were exposed to this predetermining factor. And in the other group, those were the group that were not exposed, but they still actually had that same event. So we can use this in a number of examples. Let's use the smoking example, right? So here in the relative risk formula, we'd be looking at the probability of patients who developed lung cancer, given they were smokers, divided by patients who developed lung cancer, given they were not smokers, okay? And what this formula is going to give us is a relative risk. So it's going to tell us the relative risk of those who were exposed compared to those who are not exposed. So for the smoking example, we could say that we might have a relative risk of, let's say, 5. And what that would mean is that smokers are 5 times more likely to develop lung cancer than those who do not smoke. That's how we understand relative risks, and that's what relative risks are telling us. It's telling us relative in the exposed group, how much more likely or unlikely are they to develop this event than those who are not exposed. And so like we were saying, if it's greater than 1, then the exposed group is more likely for that event to occur. If it's less than 1, then it's less likely. And if you get a relative risk of 1, that means there's no association between the two groups. So that event might not have any effect on the event occurring or not. So here we can look at the relative risk of having no health insurance given that someone lived in poverty. So let's look at this. So first of all, we have to define what our exposure is and what our event is. So the exposure would be the probability of being poor. The poverty is your exposure. And the event occurring is what is having health insurance or not having health insurance, right? So we just have to first define that. And we're asking, the question is, what is the relative risk of not having health insurance based on living in poverty, right? So in order to calculate this, we'd have to structure it in our relative risk, right, formula. So we said here, the event is, what is the event here? The event would be the probability of not having health insurance, given you were exposed. And what's the exposure? Being poor. Then let's look at the denominator. Probability of the event. What is the event? Not having health insurance, given that you're not exposed. That means that you're not in poverty, right? So let's look at how we can calculate this. We can calculate this as the probability of not having insurance, given that you're poor, over the probability of not having insurance, given that you're not poor. And we can look here at the chart. Let's try to calculate this. What the probability of not being insured, given that you're poor. Well, that we can say it's a conditional probability. So we could say it's the probability of not having insurance and being poor divided by the probability of being poor. So let's look here at our chart. We said the probability of not having insurance, given that you're poor, is 0.09%. Or sorry, 0.09, which is 9%. Right, so that's going to be your numerator. The denominator is asking the probability of being poor. So this is the unconditional probability of being poor, which if we see here is this marginal total. This is the marginal probability, which is your unconditional probability. Remember, these marginal probabilities are unconditional probabilities out here, and everything within this probability matrix is going to be a conditional probability. So here we're calculating this joint probability of 0.09 divided by the probability of being poor, which is 0.38. So here we see that the probability of not having insurance, given that you're poor, is 0.24 or 24%. So that's going to be in our numerator. Then we're going to calculate our denominator, the probability of not having insurance, given that you're not poor. So let's look at this again. The probability of not having insurance, given that you're not poor. That we could see here is 0.03, will be in the numerator. And then we're going to divide that by the probability of not being poor, which we could see here is 0.62. So we take 0.03 divided by 0.62, which is equal to 0.05, and this is going to go into our relative risk formula. So now our final calculation is 0.24 divided by 0.05, and we're getting 4.8. So now we can conclude that those who are poor have 5 times the risk of being uninsured than those who are not poor. That's our conclusion here. Okay. And we can quickly go over another example and work through it together. Okay, so here's a new example, and we could try to quickly work through this together. So this is kind of relevant in light of recent events. Imagine that the incidence of gun violence is compared in two cities. One with relaxed gun laws, which will be A, and the other will have strict gun laws. In the city with relaxed gun laws, there were 50 shootings in a population of 100,000, and the other city, there were 10 shootings in a population of 100,000. And the question is, what is the relative risk of gun violence in the city with relaxed gun laws? Okay, so what should our first step be? Our first step should be defining what the exposure is and defining what the event is. So let's do that. Let's define what the exposure is, and let's define what the event is in this case. Relaxed gun laws would be the exposure, correct? Yes, that's right. And what would be the event? The shootings, right, correct. So then we can now go about calculating this, given that we've defined both the exposure and the event. So we can put it into our formula, right? Which we can say the relative risk relative risk is equal to the probability of the event occurring given exposure divided by the probability of the event occurring given not exposed, right? So let's go about calculating this. How do we calculate this? Well, let's try to figure out what it is. So we can calculate So how do we calculate this? Does anyone have an idea? Right. So you said P the event would be the number of shootings over the population, right? So what would go in the numerator and what would go in the denominator, and how do we solve this? Yeah. So in the numerator we'd have 50 over 100,000, right? Yep. So you calculated the probability of a shooting in the relaxed gun law city, right? So that would go in your numerator. That represents the probability of the event occurring given they were exposed, right? And then we have to calculate what the probability of the event occurring given they were not exposed was. So what's that probability? Yeah, so it's the probability of the event occurring given they were not exposed. So it's the probability of shootings, um, shootings in the strict gun law city. So you calculated that to be 10 over 100,000. That's absolutely right. That's the probability in the denominator. And then you would just calculate what the relative risk is. And it's actually fairly straightforward. Don't get too confused by all the math here, because actually what we can look at is 50 divided by 100,000 over 10 over 100,000. And because you have the same denominator, it's 100,000 in both of these two cities, you don't have to worry about it. So it actually just simplifies to 50 divided by 10 is what your relative risk is. And what does that calculate down to? Yep, that's absolutely right. Yeah, so you got the relative risk, which is equal to 5. And what does that mean? What can we conclude from this relative risk? What can our conclusion, our summary statement be from this data? Yes, exactly. So since the relative risk is equal to 5, we could say that those who live in a city with relaxed gun laws are 5 times as likely to be involved in a shooting than those who live in a city with relaxed gun laws. So that's our takeaway. That's our summary statement. Is we could say that there's a 5 times more likelihood of shootings happening in a city with relaxed gun laws than there are with a city with strict gun laws. So does that make sense to everyone? All right, great. Well, I'm glad we were able to work on those 2 topics in probability. Probability can definitely be tricky sometimes, so it's always good to practice as much as possible and be able to go over the questions. If anyone has any other questions, I'm happy to answer some quick questions. I'll also be back on tomorrow at the same time and have another section. All right, great. So if there's no other questions, best of luck with the rest of the week. I'll be back on tomorrow, and hope you guys all do well on this week's homework.